Many of the others are coming because you have a coursework to submit. So we will look at the turbulence models that we discussed the other day, and then from here on we will move on to the errors that can happen in CFD simulations, and then I'll talk briefly about the exam as well, if time permits. But in January, you've been timetabled for one class, as far as I know. So I will do a proper revision session in that class rather than doing any theory. And before Christmas, I will put on Blackboard some sample questions that you can practice over the Christmas holidays, so that you will be fully prepared for your exams. Okay, so that's the plan. So I'm sure we can go according to the plan anyway. So we were talking about Reynolds average Navier-Stokes equations the other day, and all Brandt's models, they assume a Bossiness hypothesis. The Bossiness hypothesis means that rho u prime u prime, the average of that is equal to minus dynamic viscosity times da by u bar, which is the average velocity over da by x, plus da by u bar over da by I think here. Sorry, no, this is da by u, da by x actually, yeah. So that means twice this much. So with the Bossiness hypothesis, we assume this to be isotropic, which means same in all directions. So this is a simplification of turbulence or the of turbulent terms. Okay. So the other isotropic eddy viscosity models are. So if you go back, you see that your eddy viscosity model means that that is your spatial velocity gradient, and that is the average turbulence term, and that is equal to your dynamic viscosity times your average velocity gradient. So that type of models are other that type of models are the mixing length model, Spelart-Almaraz model, which we are not going to discuss here, and standard K epsilon model, and there are variants of the K epsilon model and the K omega model. So these are basically two equation models, so like the previous one. And in the K epsilon model, this is what you have been using most of the time. So we take the epsilon is the dissipation rate of K. K is the turbulent kinetic energy. So for this equation, you need a K and an epsilon. Epsilon is the dissipation rate of K, and K is the turbulent kinetic energy. So so K determines the energy. That means if your velocities are high, your energy is high, obviously, because K is the K determines the turbulent kinetic energy, so that is the turbulent part only. And epsilon determines the dissipation rate. So remember we talked about the dissipation of turbulence or dissipation of eddies. So dissipation means how quickly it disappears. The kinetic energy disappears into smaller eddies and dissipates as heat. Okay. So epsilon is the rate of that dissipation. So how fast it dissipates. So so your eddy your dynamic viscosity is given as rho times C mu k squared over epsilon. So that's your turbulence model. You need k and epsilon for this equation and the constant C as well. Okay, so these were the factors you embedded into your k epsilon model in the when you did the simulation. Some of you are still doing the simulations. So this is the simplest model. The good thing about this model is it's simple. Therefore, you get an answer quickly, and it's quite robust. So you must have seen that when you change to k omega or SST, some of your solutions didn't converge. Some of them diverged because they are complex models. Therefore, you need more iterations for that to converge. But k epsilon model is simple, and therefore it's quite robust. Okay. But the disadvantage of k epsilon model is normally it's good for cases where you don't have swirl in it. Okay, if you have swirl in the physics, it's not that good. Okay. So advantages are it's relatively simple to implement, leads to stable calculations that converge relatively easily. You get reasonable predictions for many. Disadvantages are poor prediction swirling, as I said, or if you have separation. So if you, for example, if you do a aerofoil, you might find separation, flow separation at the end. K epsilon model doesn't do that very well. Okay. And it's not good for axisymmetric jets or unconfined flows. So when the flow becomes fairly complex, K epsilon model doesn't handle it very well. And it is valid only for fully turbulent flows. You can't do it for transition cases. Okay, sorry, you can't use it for transition cases. And the equation is epsilon equation is simple. Okay. And the k omega model is the next up in the ladder. So it's again a two equation model. Omega is the specific rate of dissipation, dissipation k over epsilon. So this because of that, it solves two more partial differential equations. So it solves the k epsilon model as well as a transport equation for omega, which is the specific rate of dissipation. So here it's k epsilon model is k and epsilon are embedded in this model, in the k omega model. So you have an omega as well in addition to k and epsilon. So because k epsilon model is embedded in this one, the numerical behavior is similar to the k epsilon model, and it performs slightly better in near wall regions, and it is isotropic. Again, eddy viscosity is isotropic, so it has same drawbacks, slightly similar drawbacks as k epsilon model. And again, this one doesn't perform very well in free stream regions. Then you have what you call the Reynolds stress model. So for Reynolds stress model, you need to solve 6 independent Reynolds stresses for the transport equation, and so you need closure for the dissipation, turbulent dissipation. Closure means, what is meant by closure is when you have a set of equations, you need to have solution. So to have solution, if you don't have enough variables, so the number of variables times the number should be equal to the number of equations. So if you don't have, if there's a mismatch, you need to make an assumption. So when you make an assumption, you call it a closure. So you close the set of equations by making an assumption. Okay. So Reynolds stress model is fairly accurate because it solves more number of equations in here, and it's actually Reynolds stress model is good for better physics, like for cyclonic flows, or for swirling flows or rotating flows. Reynolds stress model is better. Okay. So in your T-pipe problem, you didn't have swirling flows, so the flow was fairly simple. So you don't really have to go to the Reynolds stress model. It's a K epsilon or a K omega model would be good enough if you had a good mesh. Okay. So a summary of the models: standard K epsilon, RNG K epsilon, realizable K epsilon, and Reynolds stress models. So in essence, all K epsilon models are fairly robust, meaning you can easily use them and get a converged solution. So weaknesses are they are too simple, therefore their predictions are also too simple, meaning it can give you a wrong answer. But Reynolds stress models are more accurate, but the drawback is when you have more accurate Reynolds stress model, more equations to solve. That means more computer time. Okay, if you have more equations to solve, you need more computer time. And this is a comparison of direct numerical simulation, large eddy simulation, and Reynolds average Navier-Stokes equation. So now this is your velocity field U, right? Now the really wiggly line is your DNS results, direct numerical simulation. So it solves it real time. That's your actual. That's more or less your actual velocity field, right? The actual velocity U. And in large eddy simulation, you even it out a little bit. You get the shape of that curve in kind of a macro level. Okay. So this, I would say, this is a micro level analysis. This is a kind of a macro level analysis. And but at the end, you fluctuates about this average line. So Reynolds average Navier-Stokes says, okay, that's my U. So you can see that DNS and LES are good. It gives you a solution with respect to time as well. But your Reynolds average Navier-Stokes equations, they don't really give a solution at different times. It gives you an average solution for the flow field. Yeah. So this is what you did for your fully developed flow in the pipe case, right? So So your Reynolds average Navier-Stokes equations give you a nice profile, but the actual profile would be that, okay? Would be that, and a fairly representative profile is given here. But here, your mesh can be as coarse as this. For your DNS, your mesh has to be as fine as this. And this is a good compromise. LES is a good compromise between DNS and RANS. Okay, here I ask a few questions, explain the Kolmogorov energy spectrum. Now, when you revise, go through the slides. They are all here on Blackboard, and there are some questions that are at the end of the slide. So, read the questions and see whether you can answer the questions using the slides before. And mind you, it's not open book, it's closed book exam, so you're only allowed to take your calculators with you and the pens, of course, and the identity card, etc. But so you need to know it by heart rather than you can't refer to your notes at the exam, okay? Because some of you may have done heat transfer, power and the environment last year, so where you had a open book exam, right? So we talked about DNS, LES, RANS, etc. just now. So I'm not going to go through these questions. So you go through them later on. Okay. So basically, you need to know the differences between your K epsilon equations and the K omega equations, etc. Read a little bit about this as well. So you can, when you run your simulations, okay, you have come to the end of it anyway. When you when you mark time for until your simulation is converged, you can go to the help of ANSYS and read about this also. There are nice notes on these on ANSYS as well, ANSYS help as well. So basically, K epsilon and K omega models have isotropic eddy viscosity, and your Reynolds stress models. It solves 7 equations and it gives you an anisotropic eddy viscosity. Okay. Right. We stop there, and brief note about your coursework. Well, use safer sign for plagiarism test yourselves. Yeah. So we don't want to find out that you have copied from your neighbor or from your you have just copied some text from Google. So you don't want to find that out. So find it out yourself and do it properly. Okay. Right. So that concludes the study of turbulence models, and then we will move on to errors. Right. So, what are errors? You can errors are you can categorize them into 2. One are actual errors. One is the uncertainty that you get from the problem from CFD. So you have numerical errors, which are truncation errors. So you know you used single precision and double precision. So in single precision, the numbers are stored as an 8-digit number, whereas in double precision, it is a 16-digit number. So, and there can be coding errors because codes are written by humans as well. So there could be There could be bugs in the software. And human errors, so you keep on typing. So 15.6 can be easily written as 16.5 or even 25.5 because 1 and 2 are near the. So you must be when you do the typing, you can make an error. Or you can use wrong conditions. For example, selecting the wrong turbulence model, etc. And then also you can have uncertainty. So you have an input value which you know is it should be the value, but you're not really certain that value, whether to use that value exactly, because your boundary conditions are also an approximation. Okay. And physical model uncertainty, meaning you have a physical problem and then you have your numerical model. So you need to be certain that your physical problem is represented by your numerical model. For example, to see whether, to know whether your combustion model is correct, whether your turbulence model is correct, etc. Okay, so you have errors and uncertainty. And then importantly, you have what you call the truncation error. Truncation error is we talked about this earlier. So that's your partial differential equation, the approximation of the partial differential equation. So when you write the Taylor series expansion of that, you have a lot of terms, but you only use second order or third order, first order, second order or third order numerical scheme, and the rest, whatever from there to the higher order, you ignore. So that's your truncation error. Okay? Your truncation error is the amount that you ignore. So your truncation error is basically the numerical scheme minus the differential equation. Okay. So here we call it. So this is a first order representation. So in here, this is your finite different representation, and that is your truncation error. So we ignore all that when your finite different representation is that. Yes. You were you asked, sometimes you ask whether, okay, my solution, my errors or my residuals go like that, and then it goes straight and like that. Okay. So after 60 steps, it has come to a level, and after 150 steps, it stays at the same level. Okay. So it's better to stop there than there, because all here you do is you are doing it again and again. So you can introduce a numerical error into this if you iterate too much. Okay, because it's all an approximation. So you can increase your error if you iterate for too long. Okay, once it's converged, once you've got a good solution, converged solution, you stop there. So your quality of your solution will deteriorate if you iterate too much. Okay. So your truncation error again occurs from the discretization scheme used. So if you have a good discretization scheme, your if you have a higher order, so you used simple method, remember? So if you have higher order discretization scheme, your truncation error is small. Okay. And your rounding off error can be minimized by going double precision rather than single precision. Right? Okay, so this is a representation of both the errors. Truncation error increases with time step. So your truncation error will be increased when you iterate too much. Okay, and round off error decreases with increased time step and mesh size. So your round off error is less when your mesh is fine and when you iterate for a long time. Okay, so that is your round off error. That is your truncation error. Okay, so the compromise is where you have you need to add it together, and that's where you get the best error, meaning the least error. Okay. So after this, if you iterate too long, your error will increase. Okay. So that would be a truncation, that would be a round off, that would be your total error. So that, okay, now this is where it converges. So stop here. Okay, so that stop here. So you don't need to go further than that. If you go further than that, your round off error will go up. So your total error will be higher. So somebody asked what is meant by a residual. Some of you still have the question, what is a residual? Okay. The residual is the difference of any quantity, u, v, w, etc. Any quantity before for two consecutive time steps. Okay, so you for a certain cell, you had u, v, w value in that cell at that time step, and when you go to the next time step, t plus delta t, for the after the next time step, you get the u, v, w values, and you deduct the previous value from the current value, and then you get the magnitude of that. Okay, so that error should be, that difference should be equal. When it comes near zero, you say it's converged. Okay, and then you have RMS residuals and maximum residuals. RMS means you have these values, you get a root mean square value. Okay, you get the root mean square value, so that gives you the RMS residuals, or you can set in the software to use a maximum value. So that will tell you the maximum value in the grid, in the total grid. So RMS value gives you an average value. Okay. Here, you see that's your for the continuity equation of x, y, z velocities. So you give you give your these are the size of the residuals that you want. Okay. So that's a fully converged solution. So so if your RFMS value is steady, you say it is converged. So in this solution also, I would stop somewhere in here. 500 is a very good point to stop here. So once you have iterated for 1,000 iterations, and if you have got a solution like this, I would run it again, just for 500 steps, starting from 0, and get that as my solution. Okay, I wouldn't go that far. Okay. And divergence means if this goes up, that's divergence. That means your solution has gone haywire, and that's not a solution basically. Okay. Divergence means these differences are going to increase with the time step. Yeah. So that's a diverged solution. Basically, it's not a solution. Your solution is diverging, means you are not going to get a solution. So, if the software knows when it converges, why don't we get the solution at that point? No, it doesn't work like that. You have to solve time step by time step to come to that level. Okay, so you don't know the end result now. So you have to do an iterative calculation to get the end result. So this is not even a question. So, for example, if this is your equation, you need to get a combination of variables which satisfies this equation. Okay. So you can have different convergence criteria as well. So it's not just the RMS values going down. You take it as you can't just take it as a converged solution. You can also use some other methods to see whether the solution has been converged. So one is like you can have Wonder points. So different points of the flow field. So if you look at that point, you can look at those points, and if you get a stable answer at those points, you can still consider that solution to be converged. I advised a few of you. So you said, okay, my residuals are not going down below 10 to the minus 4. So I said, okay, use 10 to the minus 3 if it has a converged solution, because with that grid, that is the best you can get. Okay, so it doesn't go anywhere below that. Your residuals won't go anywhere below that, but it's a converged solution. So the input uncertainties. Input uncertainties are when you do the input, you have discrepancies between your inputs and your actual physical model. So you cannot get the actual geometry sometimes, or you can have a oversimplified geometry. So for example, if you have a circle, you can never draw a circle as a mesh, can you? Because a mesh is a set of small line segments, yes, or small triangular segments, or small chord segments. Yeah. So therefore, a circle can be drawn as an octagon as well, can't you? In CFD. So that's an oversimplified geometry for a circle. Yeah. And your boundary conditions could be wrong. So for example, for your pipe case, you had a flat U velocity profile coming in. Okay. It's okay for the time being for your case, but the actual velocity profile, can you get a velocity profile like that? You can't. It has a slight profile. At least at the volts, your profile is different. Yeah. And you obviously assumed the fluid properties to be constant. So your solution was a very simplified case where you assume your fluid to be a Newtonian fluid which doesn't change at all, and no density changes, no temperature changes, etc. But real fluids, all those change, right? So if you are going to do design of fluid systems next year, you will have a nice CFD problem where we do a non-Newtonian fluid. I'm still marking those assignments. So the students simulated a non-Newtonian flow, something like an oil or blood or chocolate or custard or sauce. So those are examples of non-Newtonian fluids. So it's viscosity, mu. Remember you used mu, you changed mu in your solution. That mu is not a constant. It changes according to the shear strain rate in a non-Newtonian fluid. So you need to take that into account. So we didn't take those into account in our problem. So yeah, so those all come into input uncertainties. Okay. Then you have what you call the physical model uncertainties. So you have turbulence. So turbulence, we model it. So your turbulence model can be different, and combustion is very, very difficult to model. You haven't even gone there. Okay? Because what happens with combustion is combustion. You have a fluid particle, oxygen and fuel, and they react together, and it will produce carbon dioxide and water, and a lot of heat is generated. Yes, and that heat, because of that heat, your density, your temperature, and your velocities change rapidly. Yes, so you need to model that. So, for example, you have a flow field like that. So you have a mixture of air and fuel up to here, and that is your flame front. That is where the reaction takes place. And after here, you have a completely different chemical composition. You have a completely different temperature field, and you have a completely different energy field, because chemical energy has been converted into kinetic energy and heat energy during combustion. Well, initially to heat energy, because of heat energy, you will have kinetic energy. You need to use the energy model. You need to have an energy model for that. Yes. So, as I said, we had simplifications in our simple problems. The flow was supposed to be inviscid. That means no viscosity, and incompressible and steady. So truncation error. So we'll see how we can reduce the errors. So the truncation error can be assessed or reduced by refining the mesh and the time step. And rounding errors can be reduced or by having a larger memory, so that you can go double precision. So and convergence error can be assessed by comparing the results when the model is run to different residual tolerances. So convergence error. So if you set your tolerance to the 10 to the minus 3, and if you set your tolerance level to be 10 to the minus 5, theoretically your solution with residuals at 10 to the minus 5 should be better than the solution you got for the solution you got with residuals at 10 to the minus 3. Yes. And we talk about validation here again, and quantification of uncertainties. So how do we quantify uncertainties? So you can do what you call a sensitivity analysis. So so you can run multiple runs with different values of input data, sample from probability distributions, or you can and also you can have a bounded problem. You can have upper and lower levels of a range of boundaries. Or the best thing you can do is you can compare with experimental data. So usually, so for example, for your pipe flow problem, you had a CFD solution and you had an analytical solution to compare with. Okay, so that's what you did. So in real life cases, you may not have an analytical solution, but you may have a experimental solution to compare with. So that is where, but for example, you have a simple analytical, simple experimental solution, and you do a, and you replicate that with a CFD solution, and you get your input and output, your boundary conditions correct with correct compared to the experimental solution. Once you have got that base model, then you can use those parameters that you used for your simple problem for a complex problem. So for as you are doing in your T junction, okay. So you have a simple model in a straight pipe, and then you use those parameters. You take them to your T junction where you have a more complex flow field. Okay, so that's comparing with analytical solution, but you can compare it with experimental solution as well. And also you can look at the contour plots, etc. So what you do is you look at the flow field and the pressure field, the vector field, the velocities, etc. Then while looking at it, you can say, okay, whether this makes sense or not. Okay. For this, you need experience as well. Okay. So these are vector plots. You know how to do a vector plot by now, anyway. So we don't have to go long and on about this. Okay. And you can do streamlines as well. Okay. Streamlines are like particle paths. And you do XY plots. You did XY plots for your pipe flow problem. For example, for the exit velocity as well as for the centerline velocity, you did an XY plot. And you can do various other kinds of reports. And the primary report that the software will give you is about the iteration, or is about the residuals, basically. Okay. So that concludes the series of lectures regarding theory. So that's all that you learn from me for this year. And as for a summary of today's work, so we were talking about errors, numerical, coding, and human errors. And we talked about uncertainty, input uncertainties and physical model uncertainties. And we talked about verification of the problems, and we talked about the validation. So where you validate your results with reliable experimental data. So you verify results by looking at consistency, stability, and convergence. Okay. So, for example, verification of results means, suppose you run a simulation to for 1,000 steps, and you got a result, and when you take that model to another computer as well, and if you run it again after initializing, you should get the same answer. Yes, it should happen, because you are running the same code and you are running on the same platform as well. So you should get the same answer. You will. Right? So qualitative comparisons could be a quantitative plot, a vector plot, or a streamline, and quantitative comparisons could be XY plots, forces, moments, etc. Okay. Yeah, thank you for listening to me for the last 5 weeks, including this. Do you have any questions or concerns regarding the exam, regarding the assignment? It's the time. Yes?
I found that content actually really useful for the assignment, but obviously note that the assignment's due in 2 days' time.
Yeah.
Reflecting, do you think the assignment date is probably a bit too tight in terms of the course material? Because obviously only just, being taught or, the opportunity to...
Yeah, I appreciate that it's little tight. But with the whole year's timetable, I mean, this is the best we can do. At least I finished the lecture today so that you submit it after the final lecture. But what I have been trying to do is, because I have been in all your practice classes, so I could answer your questions individually. So I've seen most of you in my tutorial classes. So that's the best we can do. So that's why we, rather than having a postgrad or somebody to do the tutorial classes, I myself come. So the lecturer comes, so that you get the best experience possible. And also you have tutorial classes scheduled after the submission. So they are redundant, okay? So I'm not coming. You don't have to come. So after today and probably tomorrow's tutorial classes, I'm not coming to any of the CFD tutorials, okay? So if you have problems, if you have a PC or something, and if you want to continue for another week, if you have problems, you can email me, and I might be able to meet you in person, depending how busy I am. But other than that, you can ask questions regarding the exams, etc. Okay. Rest assured, I will be posting. There are exam questions anyway on Blackboard, and I will be posting some sample questions as well, so you practice them for the exam. Say that again. On Blackboard, I will sort out the Blackboard. Yeah? Thank you.